Welcome to Quantum Curious, and in today's video, I'm going to discuss atom field interaction. And I'm going to analyze this interaction using very simplistic picture of the matter and the field. So I will going to analyze this interaction using quantum theory. And in quantum theory, specifically, I will use the Schrödinger equation to calculate the time-dependent probabilities associated with this interaction. So in high schools, you might have learned that atom comprises of energy levels, and in these energy levels, electrons reside. And when electrons uh, jump back from uh, low energy levels to high energy levels, they absorb energy or photons, or when they jump or when they jump down from high energy levels to lower energy levels, they emit photons. And this can be done using multiple uh, process or using multiple steps. So, as I said earlier, I will going to model the atom using energy levels, and for simplicity, I'm going to model the atom using only two energy levels. So this is a two-level system. It has a ground state and an excited state, and the difference between these two energy levels is described by h omega. So when an electron uh, is going to it's going to uh, drop down to ground state, it will going to emit a photon of this energy, and when it is going to jump back from lower energy levels to high energy levels, that is excited energy levels, it is going to absorb all the energy of this it is going to absorb the photon of this energy. So you might be wondering that atom has in reality multiple energy levels, or in other words, um, infinite number of energy levels. So how can we model this picture of atom in practice? So it can be uh, considered in practice by driving the atom using energy level, uh, driving the atom using energy field or laser field of this energy. That is the difference between these two energy levels. So it is a very good approximation in that kind of scenario. So So this is our picture, and we are going to analyze the interaction of this kind of atom with with external field. So another way of preparing two-level system is called optical pumping, and it is usually used in many experimental settings and doing or focusing on quantum optics experiments. So we know that each energy levels with some principal quantum number n has many sublevels, or 2L plus 1 level, where L is an angular momentum associated with that energy level. So how can we reduce down that kind of manifold subsystems to only two-level system? So it could be done using optical pumping technique. So in this technique, we place the atom in an optical cavity and drive the atom using external field many times. So we know that field may be polarized, and we have mainly two types of polarization. The one is linear polarization, and the second one is circular polarization. So when the atom absorbs the photon with a right circular polarization, it jumps to it jumps to another sub-level, which is which is of +1 difference in the magnetic quantum number. So using this kind of technique multiple times, we can lock the atom in only two-level system. So this is quite interesting and quite practical to analyze this kind of subsystem and its interaction with the laser field. So this is our quantum mechanical model of our two-level system. So it is described by a state vector, and the basis we are going to use are none other than the two energy levels. So here, the basis of our system is uh, excited state and the ground state. So we are working in a two or in a two-dimensional Hilbert space, and the probabilities associated with these two energy levels are CE and CG, or they are in fact energy, in fact they are probability amplitudes, and their mod square will give us probability density. And if we integrate it over some space, it is going to give us probabilities of the atom being in these energy levels. So in this picture, we have to note that we have to be cautious that we cannot say that atom is hopping around these two energy levels. So sometimes it is in excited states and sometimes it is in ground state. That is not the actual picture according to the quantum mechanics. So we know that in quantum mechanics, the measurement plays a very crucial role in order to defining the state of the system. So before the measurement, the atom is simultaneously in these two energy levels, and it is very quite counterintuitive picture, or you can say it is a kind of nonsense, but it is what it is. So atom is simultaneously in these two energy levels at the same time before the measurement uh, takes place. So the probabilities can be calculated using using the mod square of these probability amplitudes. So atom is in the superposition before the measurement takes place. Another thing worth noting that we are going to consider the stationary states uh, before before considering anything else. But it is very quite idealistic picture because we know that atom cannot sit and atoms cannot sit stationary in one state because we have quantum vacuum around around them, and it is present everywhere. And due to the interaction of the atom with this quantum vacuum, jump from uh, they can jump from low energy levels to high energy levels, or they can uh, drop down to low energy levels from high energy levels. So in this lecture, we are going to not consider that kind of picture. We will consider very idealistic picture in which we have stationary eigenstates initially, and they are described by this as when they are acted upon by a Hamiltonian, they're going to give energies associated with these energy levels. So here H naught is time independent Hamiltonian, and the energy eigenstates associated with that Hamiltonians are stationary eigenstates. So before applying anything, the atom is in superposition of these energy eigenstates. So let's consider a more realistic picture in which we have another Hamiltonian that is called interaction Hamiltonian, and it is modeling the interaction between uh, atom and some external field, maybe a laser field. So there are some so we can tackle this problem from various perspectives. The one is that we can calculate the energy eigenvalues of this interaction Hamiltonian, and these energy eigenvalues will be going to time dependent because the interaction Hamiltonian is time dependent uh, Hamiltonian. Another picture is going we can calculate um, similar model, the probability amplitude associated with that Hamiltonian. And this is going to be very simplistic picture, and we are going to use this kind of method in our video. So again, we described our state vector in terms of these eigenbases, and now our probability amplitudes are not time independent. Now they are time dependent. So we can consider uh, that the atom is in ground state initially, and the probability amplitudes associated with that uh, configuration is given as this. So we have to calculate the time dependent parts of these probability amplitudes, and this is going to give us the probability associated with these energy levels. So we can use the Schrödinger equation to calculate these probability amplitudes. First, we have to take the time derivative of these energy of these state vectors. So there's a mistake. We have to also take derivative of these exponentials. So we are going to have four terms in total. So putting these terms back into this back into this Schrödinger equation, we are going to have this. And then after getting this equation, we have to simplify in order to get these time uh, these time-dependent probability amplitudes. So after applying some kind of orthonormality condition in previous equation, we can easily calculate these time-dependent probability amplitudes. So now we have this equation. So we cannot proceed further because we do not know the form of the time-dependent Hamiltonian, that is the interaction Hamiltonian, modeling the interaction between atom and the field. So this can be written in terms of state vector and in terms of matrices and some kind of column vector. So this is our uh, finalized form of probability amplitudes, and using these we can calculate how the probabilities are evolving under some time uh, dependent potential. So this is for today. So in the previous lecture, we are going to consider how the time dependent potential will going to change these probability amplitudes.